Hello everyone and welcome to the module PN junction diode and its applications in the course on basics of electronics. In this video we will see the diffusion of majority charge carriers, the formation of depletion region and hence of the potential barrier. Now what is meaning of diffusion of majority charge carriers? In the figure on the left you can see a PN junction and the device so formed is known as PN junction diode. As soon as the junction is formed, you can see here on the P side there are large number of holes, the majority charge carriers, and very few electrons which are minority charge carriers. But the picture is very different on N side. Here you have the large number of electrons, the majority charge carriers, and very few holes, the minority charge carriers. Thus we say a large concentration gradient is formed across the junction for the majority charge carriers. This concentration gradient causes the natural flow of the majority charge carriers from one region to opposite region. The process of natural flow of the majority charge carriers from one region to the opposite region is known as diffusion. So, the holes start diffusing due to this concentration gradient from P region to N region. They start flowing naturally. Also, the electrons start flowing or diffusing naturally from N region to P region. This flow of the charge carriers, the holes from P to N and the electrons from N to P causes the diffusion current and the diffusion current densities. The net diffusion current density is given by J diffusion is equal to JHP plus JEN. JHP denotes the diffusion current density due to holes from their region of origin P, whereas JEN denotes the diffusion current density due to electrons from their region of origin, that is N. So, JHP is the diffusion current density due to the flow of holes from P to N, whereas the JEN is the diffusion current density due to the flow of electrons from N to P. When the diffusion takes place of majority charge carriers, a region is formed at the junction on both the sides which is devoid of the holes as well as electrons. So, how is this region formed? When the holes diffuse from P to N, they meet a large number of oppositely charged free charges here, that is the electrons, and they recombine with electrons. Similarly, when the electrons diffuse from N to P, they meet a large number of holes on the P side and recombine with them. Thus, both are lost just near the junction on both the sides. This causes the disappearance of holes as well as electrons when they diffuse into the opposite regions, but the ions which are present in the P region and N region, they remain there. So, they are exposed. In this figure you can see the negatively charged ions are present on the P side, whereas positively charged ions are present on the N side. The electrons and holes are lost in this small region on both the sides of the junction. This region, which is devoid of the movable charge carriers, the mobile charge carriers, that is the holes and electrons, is now known as the space charge region. It is also known as depletion region because for the obvious reason that it is devoid of, it is depleted of the mobile charge carriers, electrons and holes. These ions are also the charge carriers, but they are immobile charge carriers. They cannot move from their places. They are fixed in the crystal lattice. This depletion region is formed. As soon as the depletion region is formed, you can see the formation of an electric field between the positive ions and the negative ions. So, here the dotted lines show you the direction of electric field from positive ions to negative ions. Here also the field will be formed between the positive ions and negative ions, and between all the positive ions and negative ions the field will be formed likewise. Beyond the space charge region or the depletion region, the regions on the n side and p side are like this. You have still a large number of electrons on n side, very few holes, large number of holes on p side, very few electrons. Electric field lines are from, we say, donor ions on n side to acceptor ions on p side. The field is produced spontaneously across the junction after the diffusion process, and it is known as the built-in field. It is formed automatically inside the diode due to the diffusion process. Now, this field stops the diffusion of holes from p side to n side and of electrons from n side to p side. How? If the holes still try to go into the n region, because the concentration has not been achieved yet equal in both the regions, and therefore, the holes will still try to go from p region to n region, and if they try to go after the formation of space charge or depletion region, they are stopped at the junction due to the large positive ions present on the right side of the junction. So, the holes come back to their own region. Similarly, when the electrons try to diffuse into the p region for achieving the equal concentration, then they are stopped at the junction due to the large number of negative ions on the left side of the junction. Thus, the diffusion process stops completely after the formation of depletion region. So, the depletion region is now known as the barrier. It acts as a hurdle in the further diffusion of holes and electrons. Now, since potential is the integral of electric field, a voltage appears across the depletion region. This voltage is shown by the dotted lines across the depletion region. This voltage is denoted by capital V suffix 0. Voltage V0 across the junction is known as built-in potential barrier or internal potential barrier, IPB in short. Now, if the holes still want to go to the n region from p region, and if the electrons still want to go from n region to p region, if the holes want to go from p region to n region and electrons want to go from n region to p region, then they need to have an extra energy to overcome this barrier. This majority charge carrier cannot go into the opposite region unless it has energy EV0, that is, E is the charge of the carrier, charge on the electron, and V0 is the value of the electric field formed internally across the depletion region. Thus, EV0 is now known as the height of potential barrier. So, unless and until the holes and electrons have energy equal to the height of the potential barrier, they cannot cross over into the opposite region. This energy EV0 is approximately half of the energy band gap in the particular diode. So, if this diode is made from germanium, then we will need to supply at least 0.3 volt of external bias to this diode in order to overcome the internal potential barrier. And if this diode is made from silicon, then at least 0.7 volt of external bias has to be provided in order to cause the holes and electrons to diffuse into the opposite regions and start the conduction. It means that once the potential barrier or the depletion region is formed, the conduction stops, and this particular diode is now known as the diode in equilibrium condition. So, in order that the diode once again starts conducting, we need to disturb the equilibrium of the diode, and that is done by biasing the diode externally. Either we bias it in forward mode or we bias it in reverse mode. Somehow we have to disturb the equilibrium so that the diode starts conducting again. We will see this in detail in the next video.